Hello, everyone. Welcome to Chapter 5, where we'll take a look at continuous variables. And what are continuous variables? Basically, these are data elements that represent numeric values that can take infinite values. These could be things like a length of stay, a charge, systolic blood pressure, or an age, or the time to code records, which we'll take a closer look at. So all these are examples of continuous variables. These are numeric values that can take infinite values, right? And so when we look at that, one of the things that we want to look at are the mean, sometimes referred to as the average. And what this is the sum of the values divided by the number of values. The other one that people often get confused is the median. It's the middle value. So it's basically useful because a lot of times we'll take the mean and say we have only two values of 102, right? That would be 102 divided by 2 would be 51. If we say the average is 51, that really doesn't tell us much. But with the median, it would be the average of the two middle values. So that's much more closer to what we want to look at. And then finally, we have the mode, which is the most frequently occurring value. The range is the maximum value minus the minimum value. And the interquartile range is the difference in the third and the fourth quarter, if you will, third and the first quarter. The variance is the squared deviation from the mean, and this is related to the last bullet point of the standard deviation, which basically is a unit of measure that measures the distance away from the mean that you calculate by getting the square root of the variance. So let's take a moment and calculate these. And as you can see, the mean, we add up the values and get 23. And then we divide them by the number of observations, which is 7, and we wind up with 3.3. To get the median, we would sort these. And the middle value here is 3. And then the mode is the most frequently occurring value, which is 2, because it's 2 times out of the 7 observations. So now to calculate the range, we would take the top value, which is 6, minus the bottom value, which is 1, and we get a range of 1. Then if we take the sample variance, you can see the calculations here, and the standard deviation of being 1.8, which is the distance from the mean, right? So how is this important in healthcare? Well, it's important if we have a bigger standard deviation. We're talking about a distance, the data is scattered much farther away from the mean. If everything is less than 2, it's much closer to the mean. So let's kind of walk through this example, and this is not something you'll necessarily have to do as an HIM professional, but it's important to understand how this information is used. And so what we're going to do is do some hypothesis testing, and we're going to compare the test statistic, if you will, to a critical value based on the alpha level. And so what we do here is we have two different types of samples. We have a one sample t-test to see if the population value is different from a standard or a benchmark. And then we can compare it to a t-distribution to determine the critical value. And it could either be one-sided or two-sided. And if we get length of stay variables and we want to determine if the population, the length of stay is longer than a standard deviation, we would determine the null and the alternative hypothesis, which it is that it is less than or equal to or greater than. And then 2, we want to set what's an acceptable type 1 error, the alpha level, which is 0.05. Then we want to select the appropriate t-test. So if we have 3.3, standard deviation of 8 from our previous sample, and then we do the math here, we wind up with a test statistic of 0.44. And then we compare this test statistic to the critical value. So in this case, it's around 0, much like the standard normal bell curve, as we can see in the figure on the next slide. So if the test statistic is more extreme than the critical value, so in other words, if 0.044 is not greater than 1.93, we do not reject the null hypothesis and conclude that the length of stay is not longer than the standard. And then we talk about how this relates to the mean. We have a confidence interval that's a range of values that's likely to cover the true population. So here's what we need to know. It's in the last set of bullet points. You would think that a larger sample size has a wider interval, but actually the mean is going to make it result in a narrower interval. And the width of the confidence level interval, if you will, is a measure of the precision and the estimate of the sample mean. So a narrower interval is more precise. So that's why we always say, if you see statistics, whether it's in sports or epidemiology, talking about a small sample size, this is why the larger the sample size, the more narrow the interval, and the outcome is that the sample will more closely represent the population at large. And you can do these if you want, but it's important to just more understand why this is important. So with their example, we have an average of 3.3, standard deviation 1.8, number of 7 observations, 95% confidence interval. So we get that 0.05 divided by 2, and then it's 0.025. So the critical value is 3.3 plus or minus 1.7. So that gives us 1.6 point, as you can see in this set of data down here. 3.3, which is the average, plus or minus 1.7. So if we add 3.3 plus 5, plus 1.7, excuse me, we get 5. We subtract 1.7, we wind up with 1.6. So in other words, we're 95% sure that the range is going to be from 1.6 to 5 days. The paired t-test is used to compare pre and post-test population or matched pairs. So in other words, we want to determine what the critical value is, and it could either be one-sided or two-sided. So in this case, this is a good one that relates to our field. When we transition from ICD-9 to ICD-10, ICD-10 is more detailed, and a lot of studies were looking at how much longer it would take to code things in ICD-10 versus ICD-9. And so first step, as we've seen before, determine the null and the alternative hypothesis. So one is that there is no difference and that there is a difference. And then we set the alpha level to 0.01. You can see our list of observations here. And then we get the test statistic and we compare it to the critical value. And when we look at this, we come up with the standard deviation of 4.2. So in other words, what that's telling us is that these observations are spread farther away from the mean. And we're comparing the t distribution with the range, so on. And so since 1.49 is not greater than 3.5, we do not reject the null hypothesis. So in other words, we're not going to say that there is no difference. So the important thing is here, not so much to do the calculations, but in our field, understand what the calculations mean. A two-sample t-test is used to test if two population means are different. Right? And so it could be either one-sided or two-sided. And that's basically what we are using it for. And that's all I have for you. We'll see you online. Please stop by office hours if you have any questions about this material. Bye now.